Welcome all to the Radiation Physics course, Lecture 3, Radioactive Decay. We'll be addressing decay energy, the decay equation and units of radioactivity here. So myself I am Mohammed M.Sc.Physics, Assistant Professor, PG Department of Physics, SyllubusI Science College. Here is my plan of talk. I will be talking about decay energy or Q value and the decay equation and the units of radioactivity. And the decay energy or Q value is the decay energy is a term used to quantify the energy released during the decay process. So we are already familiar with the many decay process, beta decay, alpha decay, gamma decay. In all that process we understood that there is a parent nuclei is there, then there is a daughter nuclei is there, and there will be an emitting of alpha particle or gamma particle or beta particle can be seen in all these reaction, and there is a generalized form of all reactions we already have seen. And once again I want to stress is that alpha is the particle with the helium nucleus, 2 proton and 2 neutron. Okay, with that I'll be starting the decay energy part. So decay energy is used to determine whether a certain decay mode for a nucleus is possible or not, whether the beta mode is all possible or alpha mode is possible or gamma mode is possible or not can be understood from analyzing the energy on the both side. Okay, on the parent nucleus side and the Y plus D part, that means daughter nucleus plus decay nucleus. So while calculating this energy on the either side, we can predict that whether the possibility of any decay mode, or the decay mode is representing the decay of alpha, beta or gamma, any such decay. That's a term used for decay mode. So here I just given a generalized form. X is converting to a Y plus D, where X is the parent nucleus, it is forming a daughter nucleus and a decay particle along with that. So if you just keep the energy on the both side, on the left side and the right side, we can say using a law of conservation of energy, the total energy before and after the decay should be equal. That means E0x plus Tx is equal to E0y plus Ty plus E0d plus Td, where E0x representing the rest energy, that is M0 c square for parent nucleus. Tx is the kinetic energy of the parent nucleus. E0y is the rest energy of daughter nucleus. Then Ty is the kinetic energy of daughter nucleus. E0d is the kinetic rest energy of decay nucleus. Td is the kinetic energy of decay nucleus. So we just assume that if the X is at rest, that means the parent nuclei is at rest, we can say assume that Tx is equal to 0. That is kinetic energy of the parent nucleus should be 0. Then we can represent each E0x in terms of M0x c square, then E0y in terms of M0y c square, then E0d in terms of M0d square. Then taking those all in the left side, then we can get the equation as we can see here, like M0x mx minus my minus md c square equal to ty plus td. So we just what we have done that we have taken all the rest energy on the left side and the kinetic energy terms on the right side. And here once again I just want to say that Tx is equal. If that's so, we can say that the both on the left and right side actually representing an energy, right? It is representing the decay energy. The right side is representing the kinetic energy, left side is representing the rest energy. So which is called decay energy or Q value. Okay, so we can say that Qd equal to, that is the decay energy equal to, in terms of Q, we can say that Tqd is equal to Ty plus Td, or Qd equal to mx minus my minus md c square. So now if you just substitute value of C here, and if you want to represent in terms of joule this Q value, that means energy in terms of joule, then we can say that mx minus my minus md into 8.94 into 10 raised to 16 joule. So it will be in a form of joule. And if you want to represent same in atomic mass unit, that means mass will be in atomic mass unit. In the above case, mass will be in kg. Then we can say the energy in terms of electron volt. That means mx minus my minus md into 931.502 mega electron volt. That will be terms. And one important factor you want to notice is that where m is representing the nuclear mass. This process is happening at the nuclear. So we can just whatever the things we are represented here, the mass will be in nuclear mass, not in atomic mass. This is one thing you have to note it. So the Q value can be either determined using the kinetic energy of the daughter nucleus and the emitter nucleus. That we already have seen that Qd equal to Ty plus Pd. So if you just know the kinetic energy released after the process, you can also get the decay energy value. So if you want to calculate, so let's substitute T equal to half mv square. Then the Td, that means the kinetic energy of decay nuclei can be represented as Qd minus half m by vy square. So how do we, that is here what we have done, we have substituted half m by vy square here, then we have taken that on the left hand side, then we will be getting Td equal to Qd minus Ty. Okay, so where the m by vy represent the mass and the velocity of daughter nucleus. So the velocity of the daughter nucleus can be determined by applying the law of conservation of linear momentum. M by vy is equal to mdvd. From that, if you substitute in the above equation, we can the last equation you can represent Td equal to Qd my plus md and then Ty equal to Qd md by my plus md, where the d is actually the Qd in that d is actually the subscript of the Q, so that is the decay energy. So this is represented in the mistaken form. So for a nuclear masses, if you are representing mass in nuclear masses, then Q alpha will be equal to mx minus my minus m alpha c square. Then Q beta can be represented mx minus my minus m beta c square. If you are just considering atomic masses, then you can say that Q alpha equal to capital Mx minus capital My minus capital M alpha c square. Then Q beta equal to Mx minus My c square. This is how we have to represent. Well, M alpha, capital M alpha representing the mass of the helium atom, not the helium nucleus mass. Here you have to substitute the mass of the helium atom, and here you have to substitute the mass of helium nucleus. Okay. So to determine if the actinium can decay through alpha as well as beta mode, this is the one question you want to address. So in order to address this question, you want to know the decay energy on the case of alpha decay and the beta decay. From that, you will be getting the idea of how decay energy is possible. So how we will just say that whether the one decay mode is possible or not. And I didn't say that, right? So we have already considered the case of an equation of rest mass energy is equal to kinetic energy of Ty plus Td, right? In that equation, the both side of equation, that the right side and the left side of the equation should be equal to, both should be positive. Then only the decay energy, that means decay mode is possible. Any decay will be possible if the energy is a positive quantity. Okay. So here also what you want to evaluate is that whether the energy is a positive quantity or a negative value. So if it is a positive quantity, the decay mode is possible. If it is a negative quantity, the decay mode is not possible. So let's examine how it works for actinium-225. So the alpha decay reaction for actinium-225 can be written as, if it is alpha decay, then 225 actinium with 89 protons can be formed to 221-87 francium, where the alpha is producing with the helium nuclear of 4 nucleons, that means a neutron plus proton with the 2 protons, right? So this is how the reaction look like for alpha decay. So then the Q value can be determined by identifying the atomic mass. So here we are using the atomic mass, not nuclear masses. So we know the atomic mass of actinium, which will be 225.023-229. Then the atomic mass of francium, 221.014-254. Then the atomic mass of helium atom. Okay, helium atom mass will be considered, that is 4.002603. Then multiply with the 931.502. So here we will be getting the Q alpha will be in terms of electron volt. So it will be 5.93 mega electron volt. Okay. Now we examine in the case of beta decay. So if the beta decay is happening, 225 actinium, then 18 protons, 225 nandy thorium will be the resultant daughter nuclei, along with the emission of an electron. That means the beta decay is happening here. This is how the reaction should be look like. Now we just examine whether the decay mode is possible or not. For that, Q beta equal to M actinium minus M thorium. Okay. So into 193.150. So here also we are considering the atomic masses. So which will be in the form of 225 023 229 minus 225 023 951 931502 to multiply with that. Then we will be getting the resultant Q beta will be in the terms of minus 0.67 mega electron volt. So since the Q value is positive for alpha decay, therefore we can say with the confidence that actinium 25 can emit alpha particle. Okay, actinium 225 can emit alpha particle. On the other hand, the negative Q value for beta decay indicates that this isotope cannot decay through electron emission. So the beta decay here is due to electron emission. We are already familiar with some other decay also. That is what is hope you are familiar with that. Okay, that is one is electron capture, one is positron decay. So here the beta decay process is with using electron emission. Anyway, so to consider whether the decay mode is possible or not, so for that you have to consider that whether the Q value should be positive. If it is negative, that decay mode is not possible. For this case, only alpha decay is possible. So now we are moving to a new section like the decay equation. The decay equation, in order to consider that what is the decay equation actually representing is that how the number of particles is converting to a number of particle daughter nuclei, like in terms of if you have number of system of a particle, so radioactive decay of a rate of decay of a radioactive nuclei in the sample depends only on the number of decaying nuclei in that sample. So how do we get the decaying nuclei in the sample? So consider a system of particles and 0 in the number at the time of t equal to 0. So we consider the time equal to t equal to 0. In that time, n0 is the number of the particle. Okay, and each of these particles has an independent but equally probability of decay per unit volume lambda, where lambda is actually representing the decay constant. We'll get to know about decay constant. Decay. How many particles are absorbed at a later time? That's the point. So if the time varies, how much the decay is happening. So the rate of decay of radioactive nuclei in the large sample depends only on the number of decaying nuclei in the sample. So if that's so, we can represent dN by dt is proportional to minus n, where dN is the number of radioactive nuclei in the sample in the time window dt. So if that's so, we can represent dN equal to with a proportionality constant minus lambda n dt, where lambda is called the decay constant. If you just analyze and get the value of decay constant, you can understand whether how much the decay is possible within a time frame. So when n of 0 is called n0, that means that n in number at the time t equal to 0. Okay, so here you can either represent in terms of lambda d means decay constant, or because sometimes we will be using lambda's wavelength also. So here I am just simply representing lambda d in terms of lambda itself, but you want to say that this is a decay constant, not wavelength. So the same equation can be further, I can represent dN by dN, which is equal to minus lambda by dt. Then you can represent d log of n equal to minus lambda t. Then if you just represent the above equation in terms of log n minus log n0 equal to minus lambda t, if you just integrate this part again. Okay, then if you take this log n equal to log n0 minus lambda t, then if you just take the exponential of this equation, n is equal to n0 exponential e raised to exponential of minus lambda t will be getting. So here you have seen a one negative sign, which signifies the number of the nuclei in the sample decreases with time. So this negative sign representing as the time goes, the number of the nuclei in the sample decreases. Okay. So how do you find the number of particles in a number of decay particles? There are two methods mainly people will be using. One of the main method is that mass spectrometry. So if the mass of the isotope in the sample is known, then the number of atoms can be estimated. N is equal to Na by Wn into Mn, where Na is the Avogadro number, Wn is the atomic weight of the radionuclide, then Mn is the mass as determined by mass spectrometry. So it is one of the methods used to identify the number of decay particles, but normally this method may not be there for in all laboratory setup. So we will be looking to further method to analyze the same. So in that one method you can identify that what is called activity calculation. So activity of a radioactive nuclear decay can be understood. From that you can identify the number of particles. So the rate of decay of the sample is measured through a particle detector capable of counting individual particles emitted by the radionuclide. So the rate of decay is the quantity called activity is called the activity. Okay. So which can be defined as A equal to minus dN by dt, which is equal to lambda dN. So A equal to A0 e raised to minus lambda by lambda dt, where A0 is equal to A0 equal to lambda d, and 0 is the initial activity of the sample. Okay. So this is how the two ways you can find the number of particles in the. So some other terms you will be noticing in the radioactive decay is that what is mean life, how to estimate the average time a nucleus would take before it decays. So which is called tau equal to 1 by lambda d. So if you take the inverse of a decay constant, you will be getting the mean lifetime of a decay in radioactive nucleus before decay. Then the radioactive nucleus half-life can be identified taking the natural logarithm of 2 divided, that means 0.693 into tau, that's the mean lifetime of into 0.693, that means ln of 2 divided by lambda d. Okay. So it is defined as the time required to the half of the nuclei in the sample to decay, that is called half-life. So we can say that in two ways. In both cases it is dependent upon the decay constant. So if you just use a technique and that you can identify the decay constant, with that technique you can identify mean life and half-life. Therefore the experimental procedure to determine decay constant can be used to find this quantity of mean life and half-life of a radioactive nuclide. Okay, what is the average time to nuclei take before decays? What is the half of the nuclei in the sample to decay? Time required for half of the nuclei in the sample to. So to verify that equation further, we can derive the equation for mean life can be weighted mean of the day time t can be represented. Okay, so here is the derivation of the mean life and half-life of radioactive nuclei. So to derive the derivation for mean life, we can take the weighted mean of the decay. So tau can be represented 0 to infinity t dn with respect to 0 to infinity dn, where n is equal to n0 e raised to minus lambda dt. So if you just substitute that in the integral equation, then the denominator becomes 0d, dn becomes 0 to alpha dn equal to minus lambda d, n0 0 to infinity e raised to minus lambda dt dt, then n0 is 0 lambda dt 0 to infinity substituted, then we will get minus n0 of the term. Then the integral in the numerator can be solved through integration by parts. So if you just take the 0 to infinity t dn, then it will be getting minus lambda d n 0 0 to infinity t e raised to minus lambda dt dt. Then further you solve this equation. The first term on the right side vanishes for t equal to 0, and at t tends to infinity, the function vanishes to infinity if the determinant derivative vanishes at the infinity. Therefore, the integral becomes 0 to infinity t dn can be minus n0, 0 to infinity e raised to minus lambda dt, then n0 lambda d, e0 e raised to minus lambda dt, 0 to infinity, then we will be getting a value minus n0 lambda d. Okay, now if you just substitute both in the equation above, in substituting this equation you will be getting minus n0 by lambda d divided by minus n0, then you can find mean life will be equal to 1 by lambda d. So now we just, since the half-life represents the time taken by the half of the atom in the sample to decay, so we can simply replace n by n02. Okay, so in the equation, so we can say we will be getting 1 by 2 equal to E0 minus lambda d t half, then e raised to lambda d t half equal to 2. From that you can get t half is equal to ln2 by lambda d ln2 tau equal to 0.693 tau. This you can just try with your own. Just represent how to do the derivation of the mean and half-life of radioactive nuclide. Now we'll just take a question here. The half-life of a radioactive sample is found to be 4 days, so 45 days. And how long would it take for 2 moles of this material to decay into 0.5 moles? So since T half is equal to 45 days, we will get lambda d equal to ln2 T half, then ln2 will be by 45, then we will be getting 15.4 raised to minus 3 K inverse. Since mole m is proportional to the number of atoms in the material, therefore we can say that the above equation in the terms can be represented m is equal to m0 e raised to minus lambda d. So here we have represented where n replaced with the mole, since the mole m, and then m0. The rearrangement of this equation gives t equal to 1 by lambda d ln m0 by m, and the time it will take for 1.5 mole for this material to decay is t equal to 1 by 15.4 10 raised to minus 3 ln 2.0 by 0.5 90. Then the answer is 90 days. Just try to do this problem, then just understood what we have done for the T half case. So these are the problems can come from half-life or mean-life problems. So here is the units of radioactivity. So the radioactivity can be measured of the material state to how many disintegration per unit volume is going to, and the unit to measure the activity of material to see how many disintegration per unit time it is going through. The unit of activity are defined in terms of disintegration per second. So it can be either represented in Curie or in becquerel. So since the Curie is the biggest quantity, so normally it will be represented in terms of Curie rather than becquerel. So 1 becquerel is corresponding to 1 disintegration per second. So 1 becquerel can be either in terms of represented in Curie 2.703 into 10 raised to minus 7. So here is the basics of decay energy, decay equation, and the units of radioactivity. So with this I will be concluding this session of lecture 3. So we'll be discussing about the source of radiation on the next lecture. Thank you all for your listening.